Okay, I think we'll get started. So today we're going to talk about the really important concept of conservation of energy. We've already talked about this way back in the second video. We talked about Noether's theorem, and in Noether's theorem we see that there's this relationship between invariants such as, or symmetries, time, space, rotation. So a time invariance or a time symmetry, very loosely speaking, the physics we do today is the same as the physics we do tomorrow, leads to a conservation law. And in the case of time invariance, it leads to conservation of energy. And this is probably the biggest concept in all of physics. If you could narrow down just one, or all of nature actually, if you had to choose just one, I think conservation of energy, you could make a good argument for that. All right, now for this course, the most natural way to categorize energy is to break it into one of two forms: kinetic energy or potential energy. Now we will see in other, later in the curriculum, we'll see there are other ways to characterize energy, but for all that we're doing, I think pretty much all that we're doing in Intro to Physical Chemistry Part 1, we will want to characterize energy this way. All right, so what this means is that the total energy, and it's this that is conserved, that's the total energy that's sitting here in Noether's theorem, is equal to the kinetic energy and the potential energy. So energy is either kinetic or potential when we break it down this way. Now, because these are added and they're equal to a constant, if one goes down, the other has to go up, and vice versa. So at any given time during the dynamics of some kind of system, kinetic energy and potential energy have their values, and those values must sum to the total. So let's just say we have some graph here of energy and position, and we just have some crazy graph here. What we can do is graph the potential energy, right? So we'll graph that potential energy, and then at any given time, we have a total amount of energy. Well, the potential energy, the potential energy at any given time is up to the graph, and then from the graph, this is the potential energy at any given, I said time, any given position, then here is the kinetic energy. So at any given position of this particle in the system, it has a certain amount of potential energy and a certain amount of kinetic energy, and they must add to the total energy. All right, well, what is the central feature of each of these? Well, kinetic energy is energy due to motion, okay, and only to motion. So every single system will have the same formula, which is kinetic energy is 1/2 mv squared, m being mass, and v being the magnitude of the velocity or the speed. So it doesn't matter what type of system we're talking about, whether it's an electron in hydrogen or atoms in a bond. What matters for kinetic energy is the motion, the speed. Okay, so this is always, always, always the same. Now, let's look at just a quick example before we go on to potential energy. So let's say we have a water molecule, and the mass of the single water molecule is about 3 × 10⁻26 kilograms. And let's just say it's moving along in whatever situation it's in, but it has a kinetic energy of 1.8 × 10⁻23 joules. Let's take our kinetic energy formula, and we want to solve for Yeah, okay, so we want to solve for the speed. What is speed? What is the speed? So that is, we want to know how fast this is going to have this amount of kinetic energy. So we solve for, we manipulate this equation, solve for v squared, then we take the square root, and now we plug in our numbers. And when we do that, we get 35.4 meters per second. That's our speed, the magnitude of our velocity. Now we don't get information about the direction of the motion. So if it's moving this way, this way, with this speed, it's going to have the same kinetic energy. So kinetic energy is a scalar quantity, not a vector quantity, and it is so simply a number. All right, well, let's talk about potential energy. Energy that is due to position. Okay, so in going back to this graph, for example, what is the value of this curve at a particular position in space? And so it's the potential energy that determines the dynamics of a system. The kinetic energy is always the same. The potential energy, the function for potential energy, so how does V depend on X, position, depends on the system. So if we have a molecule in a bond, or an atom involved in a bond versus an electron in a positive-negative charge situation, or this pen in gravity, we have a different situation in each case, and we have a different formula for the potential energy. In the next lecture, we're going to talk about some specific systems that we run into a lot and the specific functions of position. All right. Let's just finish here quickly with categorizing the types of systems that we'll run into. And we can put them into two broad categories, one being conservative systems and one being non-conservative systems. A conservative system is also called a non-dissipative system, while a non-conservative system is called a dissipative system. And the dissipative can help us, well, both of these words can help us a bit. In a conservative system, we think about the system as being, that's it, that's the whole universe. Or another way to think about it is it's in a complete vacuum. So all that there is that system. There's no interaction with its surroundings. In which case, energy is what we say locally conserved to that system. Now, the converse here, in a dissipative system, the word dissipative means we're dumping some, or we're exchanging some energy anyway, with the environment. Typically, it involves losing energy to the environment, and that turns into heat. But certainly the environment could add energy to the system. In which case, Noether's theorem and conservation of energy still hold, but in a global sense. So we have to think about both the system and its surrounding, and collectively, the system has constant total energy. So the system itself, so let's say we have just a mass on a spring, in the room here. Well, it might vibrate for a long, long time, but eventually we know it's going to stop because of the motion through the air, the friction or the drag, actually the drag through the air. It's going to slow that down, and eventually it'll come to a stop. Now, that energy is not destroyed. It's given to the air and the surroundings, and it just gets dissipated away as heat. Okay? So, in this course, we're going to talk primarily about conservative systems. Then in Intro to Physical Chemistry 2, we're going to really take a systematic approach to studying non-conservative systems. And this will lead us into the big field of thermodynamics. And then in Physical Chemistry 3, Introduction to Physical Chemistry 3, we'll come back and talk mostly about conservative systems, but a little bit about non-conservative systems as well.